Dear students, welcome to another day's lecture in elements of machine design. We were discussing about uh, helical springs. So yesterday we have seen two important formulae that are required for design of helical springs. One is the shear stress formula. Another is the deflection formula. One is formula for tau, another is formula for delta. Okay, today let us start with uh, you know finding a relation for the energy stored in a spring. We know that the springs are used for storing energy. So that is equal to, which is equal to the work done by it by the external load. See, now W is the external load. External load. Yesterday what we have seen, there the load was F. So nothing different. Only yesterday what we have seen in those formulae, uh, the load was taken as F. Today we are taking it as W here in this case. Okay, so W is the load applied on the string and delta is the deflection produced. Okay, so now assuming that the load is applied gradually, you see load is different types of loads are there. Steady load, gradually applied load, um, suddenly applied load, impact load and other things. So we are assuming that the load is applied gradually. Gradually means as at the time 0, the load is 0. As time is increasing, it's slowly increasing like that. That is gradually applied. The energy stored in the spring is the energy stored in the spring is given by letter U. Letter U is equal to half of W into delta. You see, this is the strain energy that is stored. This is the formula because of the because of the gradually applied load. Okay, so now this is the formula. In this formula, we will substitute other things and we will find out what is the energy stored. Okay, you see, yesterday we have seen one formula for tau, shear stress. This is that formula. Shear stress formula is Kw into 8WD upon pi d cube. Here we used F, so it was K Walls correction factor Kw into 8FD upon pi d cube. This was the formula that for shear stress we have derived first. Okay, so from this we can, if you take W this side on the left side, we can find the W relation like this. See, W is equal to this pi d cube will go up, so pi d cube into tau divided by 8k kwd. Okay, this is a relation for W we will substitute here, and before that we should know a relation for a delta also. Now delta also we found yesterday. Delta was 8W dm cube, that is mean diameter cube, upon number of coils into number of coils upon GD to the power 4. This was the formula we have seen yesterday. Okay, these are the two important formulae, yeah, for design. Okay, so from this, as we taken W, this now in this also let us substitute this W here, because W we can eliminate. So if you substitute like this, finally you will get like this. Okay, so here uh, yeah, what see what is remaining will be, see, d square. Actually it was d cube was there, one d will cut. Okay, d to the power 4 is 3 is here, d to the power 4 is here, so only one d will be remaining. So other things will remain like this. These are the two relations for W and delta. And then, so we will substitute these two values of W and delta in equation 1. So this is W for W, this is for delta. When you substitute like this, you will get it as um, you will get into this relation. See now, tau 2 times tau is there. Okay, so tau square it has become, and this pi and this pi. This is rearranged in such a way that tau square upon 4k square g, because 2k is also there, g. See, actually this is 8 into 2 16. So out of this 16, 1 4 is kept out, 1 4 is taken in, so it is taken as pi dn. Actually, what is pi dn? This is the total length of the wire. If the spring is opened and it is made straight, no, what will be the length? That will be pi dn, because one coil is pi d, and like that n number of coils are there. And then pi by 4 d square. Pi by 4 d square is the cross section. So actually pi dn is the length and pi by 4 d square is the area. So these two put together is the volume. See, that's why he has taken it as volume. So this u becomes as tau square upon 4k square g. This k is Wahl's correction factor, kw, okay, into volume, where volume of the spring, v is the volume of the spring, that is length of the spring into cross sectional area. Okay, like that. So you can say this is the formula for the uh, energy stored in the spring. Okay, and that what we have designed was for gradually applied load. What did we say? It is load is applied gradually, but instead of load applied gradually, but if the load falls on a spring through height h, then the energy stored in a spring will be given by this formula, not this formula. This formula u is equal to half into w delta is for gradually applied load, whereas this formula u is equal to p into h plus delta. Now in the previous formula w was the load, here p is the load, h is the height through which it is falling, and delta is the deflection. Okay, that is the thing. See, that is all. So this is okay, don't worry about this. So only if anything, no, they may ask you about the relation for the energy stored in the helical spring when the load is gradually applied, and this is the relation. Okay, u is equal to tau square upon 4k square g into v. Okay, now let us see about the design of the helical tension and compression springs. In design of helical springs, for strength, for following parameters to be considered: material for spring. In anything, any design, machine design, first we have to consider about the materials. Once we have fixed that, then spring index we have to decide. Then what is the wire diameter we have to find out. Then ends of the springs. Then arrangement of the springs for stiffness. So these are the various steps through which we should go. Now let us see the ends for helical compression springs. For helical compression springs, there are different types of ends. They are called plane ends, square ends, plane ends, plane and ground ends, square ends, square and ground ends. Okay, see like this. Uh, these are the plane ends. That means it is a spring, which is normally uh, given. See, according to the application of spring, the ends of the springs are selected. The load on helical compression spring can be maintained axially by using square and ground ends. Square and ground is, you see, in this load is coming on the In other cases, no, you see the load may not be axial, it can be tilted at an angle or something. Okay, anyway, this is the plane end. This is the plane and ground. See, this is it is plane only, but only that it is ground and made straight like this. This is squared end. You see, actually, this thing is bent and made straight like this, made square. Square means what? Axis and this are perpendicular to each other. Here also it is made, but the thing is, it is ground. Okay, some of the material is removed. If this is without removing the material itself, it is made ground. And here also it is made up and down both sides. Huh? Then squared and ground means, you see, this is squaring also they have done, and grinding also they have done. That is the thing. These are the four types of ends. Okay, inactive turns of a spring. Active turns and inactive turns. Active turns means, you see, well, first let us see what is inactive turns. Inactive, the ends of the spring which are in contact with the spring seat are the inactive turns of the spring. Inactive turns means they are in contact with the with the contact with the seat, or with the, you can say, the load itself. So therefore, they are not participating in this springing action. Inactive turns do not take any deflection of the spring under load because they are already in contact with the load. They are not, getting deflected. The number of inactive turns in case of helical compression springs depends upon the type of ends used. See which type, which of the four we are using, depending upon that will take. So now what is active turn? Active turn is the number of turns which undergo deflection under the application of load. So total number of active turns, total, see, if n dash is the total number of coils in the spring, then n, till now we have not used used this notation n. N is reserved for number of active coils or turns. That means those coils which are taking the load, external load, these the and deflecting. This is also taking load, but only that they are not deflecting. There is no deflection in this. No, there is deflection in this. That is the meaning. Okay, then P is the pitch, D is the wire diameter. So now come here. Is a type of end. If it is a plane end, plane, these four are what we have seen for here. Plane ends, plane and ground, square, and square and ground. Okay, so plane end, the number of coils is total number of coils is n dash, no? So that n dash, in plane ends, it is n. That means n dash is equal to n. That is the meaning. N dash is equal to n. Here also n dash is equal to n. In square ends, it is n dash is equal to n plus 2. In square and ground also is n dash plus n dash is equal to n plus 2. Then free length for different things, different values are given. This is Pn plus D. P is pitch, N is the number of active coils, and D is the diameter. This is the free length for it. Okay, plane and ground and a square end, it is Pn plus 3D, like that. Then solid length is N plus 1 into D, ND, like that. You see, if you remember everything, fine. If you cannot, at least you remember this thing. Total number of coils. If different ends are used, what will be the total number of coils? Okay. So these are all these end conditions, ends, what we are using. They are all for compression springs. That means those things which can be compressed. Now There are tension springs also. Tension springs also have different ends. Okay, they are formed like loops and hooks as shown in figure. Now I'll show you the figure in a moment. The helical tension springs, all coils are active, and the number of active coils is the same as the total number of coils. In this case, in tension helical springs, N and N dash are same. That's what he's saying. Okay. Hmm. See, here are these different types of ends for the tension helical springs. This is half hook. This is raised hook. So raised means, you see, this is just half of it is made straight. Here no, it is so much distance also it is raised through. Okay, and this is short twisted hook, fully twisted hook. These are different types of ends of helical springs. This is only for information sake you keep it, because we are not going to design the tension helical springs. We'll be restricting ourselves to the design of the compression helical springs only. Okay, now the arrangement of springs for stiffness and deflection. Now arrangement means, you see, due to the space limitation, in order to obtain the required stiffness at a certain deflection, the the springs are used in combinations. See, it is not that only one spring will always be used. Sometimes springs are used in parallel, springs are used in series, and springs are used in concentric fashion. Concentric means one spring inside another. You see, parallel means one beside the other. Series means one above the other, like that. Okay, let us see springs in parallel. These are the two springs which are shown in parallel. This is the normally symbolic way of representing a spring. Okay, you see, two springs are used in parallel like this. So every spring has its own stiffness K, and its own delta, depending upon how big the how depending upon what how the spring is. See, two springs can vary in wire diameter, in coil diameter, and in number of turns. Okay, depending upon that, one spring will differ from another. Okay, now F is the load, external load that is applied, and F1 and F2, these are the forces acting on spring 1 and spring 2 respectively. So if you are applying like this, you see, if two boys are standing here, one is a fat fellow, one is a very lean thin fellow. If the load is coming, it is not that it is equally coming. Is it equally coming? Hmm? Okay, let us see. If it is equally coming, we would have simply divided F by 2, we should have said. Now we are saying F1 and F2, that means the forces coming in spring 1 and spring 2 are different. Okay. Now, anyway, stiffness is different depending upon what spring we are using. K1 and K2, and delta 1 and delta 2, similarly, depending upon their stiffness, delta also varies. Okay. And this K and delta are the stiffness uh, under deflection of springs in parallel. See, if entire thing is taken as one spring, one imaginary spring, its stiffness is K, its deflection is delta. Okay. Now let us see here. Uh, the springs are said to be in parallel when the absolute deflection in each of the individual springs is equal to the deflection of the springs. You see, in this case, when they are parallel, only the delta is same. That means what? Delta 1 is equal to delta 2. That don't know equally. Now F is equal to, but the force coming is different. See, the deflection is same, but the forces are different. It's F total F is F1 plus F2, and F is nothing but K delta. So K delta is equal to K1 delta 1 plus K2 delta 2. But we know that deltas are same, so deltas can be cut. So what is remaining is K is equal to K1 plus K2. Okay, this is what is remaining. So this is in the case of parallel springs. The equivalent stiffness is equal to the sum of the individual spring stiffness. This stiffness plus this stiffness will be the total equivalent stiffness. That means these two springs are replaced by one spring. That one spring should have this stiffness. Okay, now let us see about the springs in series. See, one spring upon another. This has its own stiffness and delta. This also has its own stiffness and delta. But the thing is, load is coming, and this load is coming on this also and this also. Okay, see, if one below the other is there, this load, this also should be able to bear, and this also should be able to bear. If one is strong and one is weak, if this is able to bear and this is not able to bear, this will break. That's all, like that. So, and if this is replaced by one spring, okay, so what will be its K and what will be its delta? What will be the, this you can say like equivalent stiffness and equivalent deflection. Okay, now again the same things. Okay, here in the previous thing, deltas were equal. Here the forces are equal. So F is equal to F1 plus F2. Whereas delta is, you see, this may deflect, this may press a little, this may presses, differently. This may press a little, this may press a little. Okay, the summation of these two is the total delta. Okay, delta 1 plus delta 2 is delta. Okay, now we know that uh, delta is nothing but F upon K. Hmm? See, from where are we bringing this? See, F is equal to K delta. We said no. If delta will be F upon K in that case. Sorry. Okay. So delta is equal to F upon K. F1 upon K plus F2 upon F1 upon K1 plus F2 upon K2. But F are all same. You see, so this can be cut. So what is remaining is 1 upon K is equal to 1 upon K1 plus 1 upon K2. This is in case of series springs. The reciprocal of the equivalent stiffness is equal to the sum of the reciprocals of the individual spring stiffness. Okay, then concentric helical springs. In concentric helical springs, when one helical spring is placed inside the other helical spring, the arrangement is called as concentric helical springs or composite springs or nested springs. It is used for one of the following purposes: to obtain greater spring force, to change the stiffness of spring system at a certain deflection, and to assume the working of a mechanism, to assure the working of a mechanism in the event of failure of one of the springs. Okay, you see, concentric springs are basically springs in parallel. Yeah, they are not, spring one above the other. They are one beside the other only. Okay, they are basically springs in parallel. The coils of springs are wound in opposite direction to eliminate the possibility of interference or binding. So, yeah, see, if you see in this figure, you see these are the concentric springs. You see, one is helix angle is like this, the other helix angle will be this, like this. Otherwise, no. अभी एक स्प्रिंग दूसरे स्प्रिंग में फंस फंस नहीं जाना चाहिए. हाँ? Therefore, see why, in order to avoid binding or interference of springs, these springs are wound in opposite direction. The two concentric springs either may have same free length as in figure A or different lengths as in, see, if this has free length same, whereas here one spring has more free length, another less. So initially only load will be coming on the longer one, and after some time the other also will start taking the load, like that. Okay, okay, like that. So in this case, concentric springs, delta will be equal to delta 2 if it is equal length. Okay, but in case of unequal length, then one will have, you know, delta, the total delta may go like this, initially at this rate, afterwards much steeper. Okay, like that. These springs are used in governors of variable speed engines to take care of the variable centrifugal force. Okay, see, only for the series and parallel springs and series springs, you should know how to calculate the stiffness of the springs. If they are, sometimes they may say, I'm having one spring and I have cut it into two. Okay, initially so many coils were there, now so many coils. Okay, so initial spring was having 10 coils, now I have cut it into 4 coils and 6 coils, two different coils. What will be the stiffness? Or like that, and they may be asking questions. Okay, so such things you should be able to, only that those two formula you keep in mind. Now let us see about the leaf springs. See, leaf spring is only theory is asked, and this type of questions are sketch semi-elliptical leaf spring. You see, you will be expected to draw the leaf spring with all the different parts, and you have to name those different parts. Okay, explain the neat sketch, constructional details with the neat sketch, constructional details of leaf spring and its applications. Okay, so you draw. You should be you practice one good leaf spring diagram, and accordingly you can answer this question. Semi-elliptical leaf springs are widely used for suspension in light and heavy commercial vehicles. In car, these are used for rear suspension. Okay. The leaf springs are made of flat semi-elliptical plate. The advantage of leaf spring over helical spring is that the ends of the springs may be guided along a definite path as it deflects to act as a structural member in addition to energy absorbing device. इसी ये जब अब वो गड्ढे में गिरता है, नहीं तो स्पीड ब्रेकर आता है, तो वो कैसे उसके एंड्स कैसे उठना चाहिए, कैसे नीचे आना चाहिए, वो जो डेफिनेट पाथ में वो ऑपरेट होता है. ओके, सो और ये भी जो है ना, एक बॉडी के स्ट्रक्चर जैसा, अपना कार बॉडी के या ट्रक के बॉडी के स्ट्रक्चर जैसा, उसके स्ट्रक्चरल मेंबर जैसा वो एक्ट करने लगता है. ओके, thus the leaf spring carry lateral load, brake torque, driving thrust and shocks. You see, all these things it carries. It consists of number of elliptical plates called blades or leaves. उसमें एक से ज़्यादा बहुत सारे सेमी एलिप्टिकल प्लेट्स होते हैं. सेमी एलिप्टिकल बोले तो हाफ एलिप्स, एलिप्स जैसे. एलिप्स बोले तो पूरा एलिप्स मालूम है ना, अंडाकृति के जैसा रहता है. सेमी एलिप्टिकल बोले तो हाफ ऑफ इट. Okay, the leaves are given initially curvature or The leaves are given initial curvature or camber so that they turn to straighten under load. ये प्री स्ट्रेसिंग, इसको बोलते हैं प्री स्ट्रेसिंग, पहले ही स्ट्रेस करके रखना। फिर हाँ, मतलब कौन सा, अगर तुमको मालूम है उसके ऊपर टेंसाइल लोड आने वाला है तो उसको उसके पहले कंप्रेसिव लोड लगा के रखो। हाँ, उसके बाद जो है ना, वो लोड जब आएगा तो पहले जो है ना, वो कंप्रेशन से जीरो तक आना चाहिए, बाद में फिर टेंशन में जाना चाहिए। Okay, thereby know the stresses coming upon that machine member will be less. The blades vary in length and are held together by a bolt passing through the center, acting as a beam of uniform strength. बीच में एक बोल्ट होता है और वो जो है एक एक यूनिफॉर्म स्ट्रेंथ बीम जैसा काम करता है। The spring is clamped at the axle housing by means of U-bolts. यू बोल्ट्स होते हैं उसको पकड़ने वाले, और जो रेयर एक्सल होता है नॉर्मली रेयर एक्सल पे, मतलब ट्रक के रेयर एक्सल पे या कार का रेयर एक्सल पे जो है ना, यू बोल्ट के जरिए वो फिर क्लैंप किया जाता है। द लॉन्गेस्ट लीव्स आर कॉल्ड एज मास्टर लीव्स and has its end formed in the shape of eye, एक आंख के जैसा उसका एंड को बनाया जाता है, through which the bolts are passed to secure the spring to its supports. वो वो जो आई होता है उससे बोल्ट्स वगैरह जाते हैं। ओके, द eyes are attached to shackle provided with bursting of anti-friction materials such as brass or bronze. जैसे यहाँ पर जो है ना, वो आई के अंदर जो है ना ब्रास और रबर का, ब्रॉन्ज और रबर का बुशेस वगैरह प्रोवाइड कर सकते हैं। बुशेस प्रोवाइड कर सकते हैं काहे के लिए, वहाँ पर एंटी फ्रिक्शन के लिए, मतलब फ्रिक्शन कम करने के लिए। See, the other leaves are called graduated leaves. One is master leaf, the big one. The others are called graduated leaves. To prevent digging in the adjacent leaves, the ends of the levers are trimmed in various forms. See, अब इन छोटा वाला जो है ऊपर वाले के अंदर घुसना नहीं चाहिए और उसके सरफेस को डैमेज नहीं करना चाहिए करके उसका एंड को ट्रिम किया जाता है। The master leaf has to withstand vertical bending load, side thrust, and twisting moment due to presence of stresses caused by these loads. So it is usual to provide two full-length leaves and rest graduated leaves. इसलिए जो फुल लेंथ लीव्स जो है, आंख तो ऊपर वाले में ही रहेगा, मगर उस फिर भी और एक जो है ना फुल लेंथ लीव भी प्रोवाइड करते हैं करके बोलते हैं। क्यों? क्योंकि इसके ऊपर क्या क्या लोड्स आ रहे हैं, बेंडिंग लोड भी आ रहा, थ्रस्ट भी आ रहा है और ट्विस्टिंग मोमेंट भी आ रहा है। ओके, सो rebound clips are located at intermediate position in the length of the spring so that graduated leaves share the also share not shear share these stresses induced in the full length leaves when the springs rebound. बीच बीच में रिबाउंड क्लिप्स भी लगाते हैं ताकि वो भी, ये ग्रेजुएटेड लीव्स भी फुल लेंथ लीव्स के ऊपर आने वाला स्ट्रेसेस को बेयर कर सके। ओके, highly cambered springs provide a soft suspension, but they are also increasing tendency to jaw, that is movement about vertical axis. Flat springs reduce tendency of vertical pitching. ओके, ये तो बहुत ही ज़्यादा सी डेप्थ में अपन पढ़ रहे हैं, इतना अपने को पढ़ने की ज़रूरत नहीं। यूज ऑफ लॉन्गर स्प्रिंग गिव्स सॉफ्ट सस्पेंशन. Generally rear springs are kept longer than the front springs. मतलब rear axle के पास बड़े और front axle के पास छोटे springs लगाते हैं. This causes them to vibrate at different frequencies which prevent excessive bounce. Okay, ये अलग अलग फ्रीक्वेंसी से वो बाउंस होंगे और थोड़ा सा कुशनिंग इफेक्ट उनको मिलेगा। Okay, this is about the leaf springs. सी, ये जो डायग्राम है, ये डायग्राम तुमको ड्रॉ करना है, प्रैक्टिस करो। सी, ये जो है ना, पहले वाला ये मास्टर मास्टर लीफ है। ओके, ये वाला देख रहे हैं, यहाँ लिखा हुआ है। और इसमें बाकी ग्रेजुएटेड लीव्स है। और यहाँ पर एक यू बोल्ट है, देखो इसके अंदर से जाके ऐसा यू बोल्ट यहाँ पर उसको नटों से टाइट किया है। और यहाँ पर एक सेंटर बोल्ट भी है। ओके, और रेयर एक्सल इसके अंदर से जाता है। और ये फ्रेम है, देखो। और ये आई है, आई के अंदर रबर बुश प्रोवाइड किया है। ओके, और ये जो है, ये वाला और ये वाला, ये रीबाउंड क्लिप्स है। ओके, एंड इसको शैकल बोलते हैं। बस इतना प्रैक्टिस कर लेना। ओके, नाउ लेट अस सॉल्व a simple problem initially. Only one problem we will take today, and then we will close this. Okay. Okay. A closed coil helical spring is used for front suspension of an automobile. The spring has stiffness 90 Newton per mm square mm. Stiffness is Newton per mm with square and ground ends. You see, square and ground ends बताया है. Okay, the load on the spring causes total deflection of 8.5 millimeter. ये डेल्टा होता है. Making by taking permissible shear stress of the material 450 MPa. Permissible shear stress tau है, 450 MPa बहुत ज़्यादा दे दिया उसने. Okay, anyway, find the spring wire diameter, that is small d चाहिए. और length of the spring. Length of the spring बोले तो फ्री लेंथ फाइंड कर लेंगे. हाँ, ओके. See now, assume spring index is 6 and G is 80 into 10 to the power 3 Newton per millimeter square. So these are the things. See, for squared and ground ends, inactive number of turns is 2. Inactive number of turns बोले तो n dash minus n जो होता है वो inactive number of turns होता है. Squared and ground ends के लिए inactive turns 2 होते हैं, क्योंकि एकदम वो सीट को चिप करके, वो लोड को चिपक के रहते हैं, तो वो कुछ डिफ्लेक्शन लेते नहीं. ओके, ओके. नाउ we have spring stiffness is load upon delta. Okay, so therefore F is equal to K into delta. Okay, K is the spring stiffness. This is given 90 into 8.5. Okay, this is 765 newtons. And Wahl's correction factor, we know Wahl's correction factor Kw is 4c minus 1 upon 4c minus 4 plus 0.615 upon c. So ये 6 तो दिया है स्प्रिंग इंडेक्स c. सो 6 जब डालते हैं तो 1.2525 आता है. ये हमेशा इतना ही आता है, याद रखना. अगर तुमको 6 अगर आता है तो ये वैल्यू इतना ही आना चाहिए, 1.2525. ओके, then shear stress induced. Now one formula that we are using here is that formula. Two formulae are there, one is for tau and one is for delta. Both we are going to use. ये formula के अंदर तुम अगर substitute करोगे हर चीज, यहाँ से तुमको diameter आ रहा 6. ओके, 5.7 आ रहा है, उसको राउंड करके 6 कर देने का. उसके बाद अपने को लेंथ भी चाहिए. लेंथ के लिए अपने को डेल्टा चाहिए. डेल्टा जो ना, ये वैल्यू है. You can put it in terms of c. Okay, instead of d, capital D. Okay, because c मालूम है अपने. ओके, सो इसमें से नंबर ऑफ टर्न्स आते हैं. नंबर ऑफ टर्न्स के लिए अभी नंबर ऑफ टर्न्स को इसको अरेंज करो, इस तरह आता है. इसमें से 2.9 आ गया, सो 3 अपन ले लेंगे. 3 नंबर ऑफ टर्न्स. सो डी आ गया, वायर डायमीटर आ गया, नंबर ऑफ कॉइल्स आ गया. तो लेंथ ऑफ द स्प्रिंग इज, फ्री लेंथ ऑफ द स्प्रिंग n dash d plus delta maximum plus 0.15 delta. Now n dash जो है ना Now n dash is the total number of coils is n plus 2. Okay, this is for squared and ground ends, इसलिए n तो 3 आ गया और दो इनएक्टिव कॉइल्स हैं, टोटल कॉइल्स 5 हो गए. ठीक है. सो लेंथ ऑफ द स्प्रिंग विल बी this is the thing. See, n dash into d, n dash is 5 and d is 6 from here, यहाँ से आए. हाँ, और डेल्टा मैक्सिमम 8.5 है. डेल्टा मैक्सिमम 8.5 ये तो फिगर में दिया हुआ है और प्रॉब्लम में दिया हुआ है, और 0.15 ऑफ डेल्टा मैक्सिमम. दिस इज द फ्री लेंथ ऑफ द स्प्रिंग. इसी लेंथ ऑफ द वायर बोलते तो अलग होता है, लेंथ ऑफ स्प्रिंग बोले तो अलग होता है. लेंथ ऑफ स्प्रिंग बोलते तो फ्री लेंथ, लेंथ ऑफ द वायर बोले तो है ना, उसको पूरा स्ट्रेच करके जो पूछते हैं, जो कौन जो गिनते हैं, वो लेंथ ऑफ द वायर हो जाए. ओके, so this is one formula we have solved. So today we will stop here. Okay, and we will solve some more problems tomorrow. Thank you.